Hello, algebra students. This is an introduction to graphing linear equations. This is section 3.2 in our textbook. Let's begin. All right, so a little backstory to what we are doing. We have been dealing with equations for a while now. Equations that we are dealing with have an x and a y in them. The a, b, and c would have numbers in for a, b, and c, but the x and y would stay our variables. Something like 2x plus 3y is equal to 12, for example. And what we are trying to do when we graph something is, and the graphs will look like this with an x, y, grid on them. What we are trying to do is we are trying to say, hey, where are the solutions to this equation? There are actually infinite solutions, and you guys, I believe, would be able to come up with some of them. For example, let's do that. If I were to plug in 0 for x, there still is a y value that makes this true. This didn't exist here. The y value that would make this true would be 4. Do you guys agree with that? If I plug in 0 for x, this becomes 0, and 3 times 4 is 12. So that's one solution. There are others, though. For example, if I plugged in 0 for y, if I plugged in 0 for y, this would go away, and then 6 would be the x value that would make that true. Let's find one more. Let's just say I plugged in 3 for x. If I plugged in 3 for x, this becomes 6. 6 plus what is 12? Well, I would need to add a 6 here. And that would be the y value of 2. If I plug in 3 and 2 for x and y, this is 6 and that's 6, and they both add to 12. So these 3 points are called solutions to this equation. When we graph them in a number line, 1, 2, 3, 1, 2, that's 1. 6, 0 would be out here, and 0, 4 would be over here. When we graph them, something interesting happens, and that interesting thing is they form a line. And this line extends forever, and it would show all of the solutions to this equation. If that dot is on this line, even out here somewhere, if it's on this line, it's a solution to this equation. If it's not, it is not a solution to this equation. So the purpose of graphing is to say, hey, where do all of the points that make this equation true exist? So how do we do that? Let's look at an example. Our first example is going to be negative 2x plus y is equal to negative 3. There are going to be some tasks that I ask you to do to graph these equations, and the first one is going to be solve for y. Now, we've been practicing solving for y. In fact, your last quiz, one series of questions said solve this equation for y. What it's saying is get y by itself. Well, y has a negative 2x on the same side as it. How do I move a negative 2x? Hopefully you are yelling at your computer screen. You add 2x, right? That's what's going to move a negative 2x. And what we end up with is y is equal to negative 3 plus 2x. So that's step 1, get y by itself. Step 2 is going to be to plug in or create the t-table. We'll call it create the t-table. And when I ask for a t-table, what I always want is the same x values. This is x, this is y, and I want you to plug in negative 2, negative 1, 0, 1, and 2. That's very common as the 5 points that you want to plug in. So what this is going to look like is these are the x values. First, you're going to start with negative 2, and you're going to plug negative 2 in for x in this solve for equation. What that would look like would be y is equal to negative 3 plus 2 times negative 2. We are smart and we follow order of operations. So the first thing we would do is this multiplication. And when we multiply those, that would be negative 4. And we would end up with negative 7. So when we plug in negative 2 for x, what we get out for y is negative 7. And we're just going to do this 5 times, and then we'll get faster. Next, I'm going to plug negative 1 in for x. That would be negative 3 plus 2 times negative 1. Well, you know negative 2 or positive 2 times negative 1 is negative 2. So that would be negative 5. Up next would be 0. 0 is the easiest one to plug in. When you plug in 0 for x, this just goes away, and you're left with negative 3. What about when you plug in 1 for x? You just have negative 3 plus 2, right? Because 2 times 1 is just 2. And that would give you negative 1. You should be seeing a pattern here. It's adding 2, adding 2, adding 2. We should be able to see that our next point is going to be 1, 2 comma 1. But we could verify it to make sure. If I plug in 2 for x, this would be 4. And negative 3 plus 4 is 1. So these are the points that I have to plot. Negative 2, 7 would be up here. Negative 1, negative 2, negative 7 would be down here. Negative 1, negative 5. 0, negative 3. 1, negative 1, and 2, 1. So as you can see, these are going to form a line, which is fantastic news for us. That's exactly what we want. If we are doing this and somehow it doesn't form a line, that's exciting. If it doesn't form a line, that tells us that something is wrong. Probably your math somewhere along the way. And check the ones that are not on the line. That's going to be a really easy way to fix that. Let's move on to this one. This is the same level of difficulty, so I think you guys should be able to handle it. Go ahead and pause it here and try at least the first step, which is to solve for y. Solve for y. Y needs to be by itself. It has a plus 3x happening to it, and the way that we undo that is we subtract 3x. You could have written it like this. You'll see math teachers in the book and stuff always put the x term first. But if you had y equals 2 minus 3x, that's the same thing. These are the exact same. The 3x is negative and the 2 is positive. It's going to benefit you to get in this habit, but you don't need to be there right now. And by this habit, I mean writing the x term first. Up next, you would plug in negative 2, negative 1, 0, 1, and 2 for x, which seems exciting because it is. You plug in negative 2 for x, that would be negative 3 times negative 2 plus 2. Negative 3 times negative 2 is positive 6, and 6 plus 2 is 8. Then you can plug in negative 1. Negative 3 times negative 1 plus 2. Negative 3 times negative 1 is 3, and 3 plus 2 is 5. Then you can plug in 0. Negative 3 times 0 plus 2. We know negative 3 times 0 is just 0. Plus 2 is 2. Negative 3 times 1 is negative 3. And negative 3 plus 2 is negative 1. Once again, we're seeing a pattern. Subtract 3, subtract 3, subtract 3. Our next one is going to be negative 4. If we're doing it right, negative 6 plus 2 is negative 4. So then I'm going to plot these just the same. Negative 2 comma 8 is up here. Negative 1, 5, 0, 2, 1, negative 1, and 2, negative 4. We're going to see that they form a beautiful line, even if I can't draw one. And that is our equation. Remember, what this means is that every point along this line would make this equation true. If it's not on that line, somewhere here or here, then it's not going to be true. This one is a little bit more difficult because solving for y is more difficult. So let's take a minute to try to solve this equation for y. Y is not by itself. Of course, it has this positive x by it. In order to move a positive x, we're going to subtract x, giving us negative 2y is equal to 6 minus x. Our next step, y is being multiplied by negative 2. How do we undo a multiply by negative 2? Well, we divide by negative 2. That was not what I intended to do. Just trying to get this out of the way. Divide by negative 2. If we divide one side by negative 2, we have to divide the other side by negative 2. What we'd end up with is y is equal to, I'm not going to simplify this. I am going to expect you to simplify this shortly, But for today, let's just leave it 6 minus x over negative 2. That's our first step, and our second step is to create the t-table x, y, negative 2, negative 1, 0, 1, and 2. This is going to be a little bit more challenging, and we're going to have fractions, but that's just what's the reality of it. It's going to happen sometimes. If you plug in negative 2 for x, you'd have y is equal to 6 minus negative 2 over negative 2. 6 minus negative 2 is 8. Minus a negative turns into plus. And then we divide that by negative 2, and we get negative 4. Carrying on, plugging in negative 1, y is equal to 6 minus negative 1 over negative 2. 6 minus negative 1 is 7, and 7 over negative 2 is negative 3.5. Plugging in 0, 0 is always the easy one. 6 minus 0 is just 6. And 6 over negative 2 is negative 3. Up next, we've got 6 minus negative 1 over, 6 minus 1. I'm off with my negatives today. 6 minus 1 over 2, negative 2. 6 minus 1 is 5, and 5 over negative 2 is negative 2.5. One of those things where I think we're seeing the pattern again, and the next number is going to be negative 2, but we can verify it. 6 minus 2 over negative 2. 6 minus 2 is 4, and 4 over negative 2 is negative 2. So now we've created the t-table, and now we plot it. Negative 2, negative 4, negative 1, negative 3.5, 0, negative 3, 1, negative 2.5, and 2, negative 2. You're going to notice it is in a line again. It's very all together, but that is a nice line. We're going to connect it, and that is our graph. I do have 2 more examples, and they're kind of weird. These are going to be examples where it only tells you x equals a number or y equals a number. So remember back at the beginning, I'll just go there. What we're doing is we're finding x, y values that make an equation true, right? 3, 2 made this equation true. 0, 4 made this equation true. Well, when we look at this example, the only thing that we know is that the y value is negative 2. That's the only thing we know. What are some points that the y value is negative 2? Well, 0, negative 2, right? That's a point. The x value is 0 and the y value is negative 2. Well, what's another point where the y value is negative 2? I mean, you guys should be able to think of an infinite amount of them. 5, negative 2. Negative 2, negative 2. Negative 6, negative 2. Let's see, right? All of these would work for this equation. We don't know anything about the x value, but we do know that the y value is negative 2. And the y value is negative 2 for every one of these points. Let's plot them and see what they look like. 0, negative 2 is right here. 5, negative 2. Negative 2, negative 2. Negative 6, negative 2. We should be seeing something happen, right? This is forming a line. This is the line for him to connect them where the y value is always negative 2, right? That's what we know has to be true. The y value is negative 2 literally everywhere along this line. The x value is changing, but the y value is negative 2. Let's do one with x, just the same. This one is saying that the x value has to be 5. So pick some points where the x value is 5. 5, 1. 5, 0. 5, negative 3, right? This is true that the x value is always 5. I don't care what the y value is. I just know the x value has to be 5. I can plot them 5, 1, 5, 0, 5, negative 3, 5, 6. What we're seeing is that this line right here is the line where the x value is always 5. I know this is a really ugly line, but if you just pretend, use your imagination, it would be prettier. Everywhere along this line, the x value is 5. That's what we're looking for. So that's all I have for you guys for graphing linear equations. Please let me know if you have any questions, and good luck.